everyone, welcome to video recording number 6, where we will continue from where we left off previously. In this recording, I will focus on discussing semi-crystalline polymers in terms of their microstructure, morphology, and mechanical properties, followed by phase transitions and the equilibrium considerations for melting and crystallization. Now, a semi-crystalline polymer is important because, like I mentioned, all crystallizable polymers that we have in the market right now, or in the industry right now, are of this variant, semi-crystalline polymer. So we need to look at its microstructure, its morphology, and how these two components combine together to affect the mechanical properties. So let's take a look at the microstructure, which can be described as crystallization, which is a process combined from nucleation and the lamellar growth. In terms of nucleation, what we have here is we can have two different types of nucleation processes: heterogeneous or homogeneous. Heterogeneous nucleation comes from the surface of impurities, whereas homogeneous nucleation comes from aggregation of polymer segments below the melting temperature. The number of nucleates depend on the cooling rate of your polymer. If it's fast, you have less nucleates. If it's quick, you have more nucleates. When polymer aggregation is below a critical size, it is reversible. Above this critical size, the free energy of the system will undergo a net decrease. Nucleation typically occurs in the intact ordered regions after melting, and so once you melt your material, you let it cool down, you have the heterogeneous or homogeneous nucleation processes, and this is the bulk, and these two processes are the bulk process or dominant effect in bulk crystallization. The crystal lamella can grow differently through random re-entry, which is what I've shown you in previous recordings when I was discussing about the switchboard re-entry model in Introduction to Polymers. Or we can have adjacent re-entry through a smooth regular chain fold or a rough fold surface. Folded crystals grow by length and breadth, but not thickness. So that is why when you have longer polymer chains or longer repeating units in polymer chains, it is the melting temperature will decrease because you are less likely to form a good or a well-structured crystal lamella. The long parts, when they start to go back into this rigid 3D structure, would be sticking out either through the random mode or the rough fold surface or the smooth chain folds. So if they are longer, it's more likely they will go in as a random re-entry or rough fold surface, and that's why long repeating units would result in lower melting temperatures. Now, holding these amorphous regions and crystalline lamella in place or together is this thing called the time molecule. Now, the time molecule is important because it determines the mechanical properties of your polymer, of a semi-crystalline polymer. Now, crystallization can be varied based on your processing method. If you use melt crystallization, that means you heat up a polymer and you let it melt. What happens is the amount of polymer chains are significantly higher, and you have long ribbon-like folded chain structures, which is your lamella. And what happens here is your crystallization rate is higher, is faster. As a result, the lamella are growing close to each other. There is a possibility of a long chain or single molecule incorporated into different crystallites. So you could have a long chain that is part of a lamella A, and then another part of the same chain is the tie molecule, and the end part of this chain ends up in lamella B. Another way to make crystals is to use dilute solution crystallization. Here in this process, the number of polymer segments are lower, resulting in a slow crystallization rate, which gives you small pellet or plate-like single crystals, which are about 15 micrometers in size and 150 microns in thickness. In terms of morphology of a semi-crystalline polymer, it is governed by two main effects, or two main processes: the crystallization effects and the aggregation of crystallites. Let's take a look at crystallization effects. So in terms of crystallization effects, they can be varied based on the fabrication method. If you use extrusion, fiber spinning, or injection molding, whereby there is stress-induced chain orientation, what you have is an elongated crystal aligned in the flow direction, and there's orientation along the long crystal axis. This will provide nuclei for growth of folded chain lamella, and then this lamella would be parallel to the molecular axis of the parent fiber. Now this is different from the lamella's orientation itself. Okay, and this results in roll structures. If you use heat to stretch a polymer between the Tg and Tm, the glass transition temperature and the melting temperature, you break up the lamella. You allow the formation of chain blocks connected by microfibrils, which can be between 60 nanometers to 2 micrometers wide. And these microfibrils are between blocks, the crystalline blocks, and amorphous regions. These are the tie molecules, chain ends, and chain folds. The tie molecules, like I mentioned earlier on, is key for structural strength. The aggregation of crystallites starts initially from a rod-like nuclei, which appears to be like a sheath here in my slides. What happens subsequently is you will have a tree-like structure from both ends of the nuclei. When this tree-like structure grows and grows and comes into contact with each other, you form a spherulite. Okay, the number of lamella in these structures are different. When you still have a nuclei, number of lamella is low. When you have spherulites, the number of lamella is high. Now the morphology is heavily dependent on the crystallization rate, also known as the cooling rate. At fast crystallization rates, what happens is you will have a polymer, a semi-crystalline polymer with dynamic properties. For example, over time, your polymer may become brittle, in a very gradual fashion. So what happens is when you freeze your polymer chains quickly in position, there might be a large free volume between them. And over time, as the polymer chains come closer to each other, as they attempt to reach an unachievable thermodynamic equilibrium, the free volume becomes smaller and smaller, and then you may have subsequent gradual embrittlement. Another reason for gradual embrittlement comes from secondary crystallization, where there is progressive segregation of low molecular weight matter from the polymer chains. This low molecular weight matter may include stabilizers, catalyst residues, comonomer units, and branches. These low molecular weight materials can diffuse together in polymers made